Okay, Bismillahirrahmanirrahim. So today we are on to the 9th lecture, and we are actually dealing with the Metropolis, Hastings, and Gibbs. The topic of our discussion is MCMC, Monte Carlo Markov Chain algorithms, and we have laid the foundation for them. We'll do a bit revision before clearing the concepts, and then we will immediately start with the Metropolis Hastings algorithm. Okay, so we'll come to this slide later on. Okay, so we can do this now. I showed this in the last class as well. We discussed the concept why we are using MC and MC. First of all, we discussed the concept of Monte Carlo sampling. So we did that in detail. And then we saw why we need the Markov chain concept. So we'll go through that again. So the algorithms for the MCMC, they define different ways of constructing the Markov chain. So Markov chain is a very old concept, but now we are applying that to sample the posterior distribution. These algorithms are sensitive to their starting point. So because the point is you are going to sample repeatedly from a distribution and then move in a direction based on where you were in the previous timestamp. That is the Markov chain, right? कि आपने जो भी अगला कदम उठाना है वो उस बेस पे होगा कि आप currently कहाँ पर खड़े हुए हैं. So इस तरह आपकी search आगे बढ़ेगी. ठीक है? So we are going to be seeing the detail of that today, कि how that happens in Metropolis Hastings. It's very important for you to understand that. ठीक है? The point is कि इस तरह search करने में the initial number of sampling जो आप करते हैं for some iterations, let's say for the initial 50 iterations or the initial 100 or 200 iterations, maybe the samples are not like representative samples because they are finding their way. They are trying to make sense of what is happening. इस तरह उसको कह लें. So therefore, they are not reliable samples कि आप उनकी base के ऊपर कुछ कर सके unless the problem size is very small. ठीक है? So हमारा जो problem हम लोग discuss करें, we are discussing multivariate distributions in which we are going to have multiple columns, and we are targeting, we want to sample the posterior based on that setting. यानी हमारा जो हमारा posterior distribution है, that is actually the multivariate distribution. So that's it's not easy to sample from directly, right? So therefore, the algorithms of MCMC, इसमें ये बात you have to be confirmed कि this often requires a warm-up phase. So that it is possible that initial several iterations are not useful for you. In other words, the samples that have been obtained in those iterations are not useful. So that is, you can also call it the burn-in phase. So they can be discarded. So ये इसको आप discards कर सकते हैं until the search move towards a fruitful part of the whole search space. Okay. So initially, just like you go to a new country, right? So in the first week, you are just nowhere. आप देख रहे हैं कि where are the shops and where should I buy this, and where is the train station, blah blah blah. So that's that kind of thing. Once you find your way, then it is very easy for you to move around, and everything becomes probabilistic. तो जब आप किसी दूसरे शहर में जाते हैं तो पहली दफा किसी जगह पे जाते हैं तो आपका जो probability density is not well defined because you have not experienced anything, right? But once you have passed the week there and you're doing different iterations, then you are absolutely sure कि what's my probability density function, कि मैंने what is my probability of going from here to the train station in 5 minutes, in 10 minutes, 15 minutes, what is the probability that I'm going to return home at this time. हर चीज आपकी probability define हो जाती है through experience. So that is exactly the thing that we are replicating here. ठीक है? So just keep this thing in mind कि whenever we are sampling from the posterior distribution directly, we are not like estimating the posterior from the likelihood and prior. In fact, we are using the likelihood and prior to sample from the posterior distribution. So in other words, we are estimating the sampling distribution directly, rather than saying कि हम उसको likelihood or posterior से estimate करें. It's not like that. ठीक है? So just keep this thing in mind. Okay. Now this starts the thing. You got to be really attentive right now. So in the Bayesian model, जो कि आजकल हम पढ़ रहे हैं, we have seen the hands-on with the PyStan. And I discovered the new library which is much better than PyStan. In fact, I can't say it is much better. The PyMC library or the Python Monte Carlo या Markov Chain library आप कह लें, इसके different versions हैं. Currently, I think it is at version 4 and PyStan. So these two libraries are being used in Python to actually do this MC sampling from the posterior. This is more comfortable for you because in this one you have to write the code in C. You have to define the model in C language like we saw in the last class. In this case, it is directly Python. So I think it's really more convenient for you, but I don't think so you can distinguish between them. It's maybe you're also using Python code here. It's just a difference of the model. So there's not a lot of difference, but PyMC they have defined a lot of new functions which are very important might be important for your project. Okay. So in Bayesian statistics, we want to estimate the posterior distribution. I hope all of you are now clear on that. We cannot estimate the posterior directly. Why we cannot estimate it directly? Because posterior equals to likelihood into prior divided by the evidence. Now, if I want to calculate the evidence, I would require information about all the possible values which this can take. So I don't have that information in advance to calculate this evidence. So what we do is in the case of MC sampling, we work with ratios. We try to work with ratios. हम ratios पे काम कर लेते हैं. तो ratios के अंदर होता है कि this likelihood gets eliminated. We don't need to actually do anything. Or I will tell you the algorithmic sense behind that. कि जैसे आपने PyStan में देखा कि if you want to use MC, then you have to specify the likelihood function and you have to specify the prior function. That is based on your own experience and knowledge. We don't have that many probability distributions, right? Like we have a binomial, we have the beta distribution. Primarily, we have the Gaussian distribution. Then we have the multivariate Gaussian distribution, etc., etc. We have just maybe you can say at the most 5 very famous distributions from which you are going to specify the likelihood function and from which you are going to specify the prior function. This will come with experience. This is not going to come immediately. You are going to try out different things and then you are going to be working with that. But we have to specify that. We are not bothered with the evidence now because it is not computationally possible to compute that because we don't have the idea of the whole sample space. We can't identify all the possible values which can be taken up by the posterior, the conditional values, and we can't just measure. We can't just estimate the evidence very easily. So therefore, we just ignore this. Even in the MC case, जैसे मैंने आपको बताया कि हम ratios पे काम करते हैं, जिसमें हम we can easily eliminate the evidence from the calculation. So it's better to listen to all these things very carefully. We want to estimate the posterior distribution, but this is often intractable due to the high dimensional integral in the denominator, which is called the marginal likelihood. जिसको हम evidence कह रहे हैं. So this is called the marginal likelihood. And I have to basically integrate over all possible values which the posterior can take. And I do not have that data in advance with me. Even if I'm able to sample that, it might be a very large number of values and it is not intractable to compute that. It's a very high dimensional integral. So therefore, I do the opposite, जो कि मैंने आपको बताया, ठीक है? So we can approximate the posterior, that is p theta given x, or you can say p x bar given x. Okay? If we can somehow draw many samples that come from the posterior distribution. So that is the idea. The idea is that I draw samples from the posterior to estimate the posterior. सही है? तो MC helps me do that. In the end, I want the posterior. For example, the probability that the class is this, given the data. Probability that this guy should be labeled as fraud, given the data. Probability that this guy should be labeled as, should be given the loan, given the data. Okay? Probability that this guy should be targeted for marketing, given the data. That is the posterior that we want to estimate. Now, I estimate to estimate the posterior, I sample directly from the posterior distribution. So yeah, that is the main essence जो कि आपको बताना है, based on the information of the likelihood and the prior जो कि आप problem formulation में देते हैं. So you specify the likelihood and the prior functions. You might be wrong. ठीक है, मैं ये नहीं कहता कि you are going to be accurate on the first go. So in a very simple problems like coin toss and all those childish games, so you will be getting very perfect results. But when you go to complicated problems, then you have to adjust the parameters of this MCMC process before you can acquire the true representation of the posterior distribution. इसको please ध्यान में रखिएगा, ठीक है? That is a thing. So we can approximate the posterior if we can somehow draw many samples that come from the posterior distribution. Okay, so that is the thing. Achha, by the way, the likelihood is the, iska jo integral hota hai, the integral over the theta given s into probability. So this is basically the probability of x. So probability of x निकालने के लिए, I need to have the value of all possible thetas that can be there, because to find out probability of x, I have to integrate over all possible values of theta or the parameters जो कि मैं estimate करना चाह रहा हूँ, ठीक है? So that is not always possible to do that computationally, वो इतना feasible नहीं होता, ठीक है? That is the big thing. Okay. तो theta here basically means के I am primarily the model that I'm estimating, the probability density function that I'm estimating. Okay, you have to envision the posterior as a PDF, and I'm sampling from that. I'm sampling data from that PDF based on the values of likelihood and the prior and the parameter functions that you are giving. So I am estimating data from that PDF. The point is that I will need information about all possible values of theta to estimate the marginal likelihood, which is not possible for me because I am already getting those values based on sampling. So इसलिए हम उसको ignore कर देते हैं. So this is a potential question that I can ask in any quiz. ठीक है, तो इसको please आप ज़हन में रखिएगा. With the vanilla Monte Carlo, which we have already seen, we need the samples to be independent draws from the posterior distribution. ये हम already करके देख चुके हैं कि Monte Carlo does sampling independently. Okay, which is a problem if we do not actually know what the posterior distribution is. I mean, there is a possibility that I know the Bayesian formula, and based on the Bayesian formula, if I tell you the prior and the potential likelihood function, then it is possible for you to sample from the posterior. The algorithms have been designed in that way. In the case of pure Monte Carlo, it is not possible for me because I am sampling independently. So to estimate the posterior, the search has to be guided in a particular direction. ऐसा नहीं हो सकता कि I have this big bag of balls, ठीक है, and I sample one and calculate some parameters, then I sample, then I sample, then I sample. So all of these are independent. I can't reach the posterior with this. Rather, the search has to be guided. First I go here, okay, then I go here, then I go here, then I go here. The search has to be guided because it has to be a directed search and not a random independent search. It is possible कि मैं इसके through भी मैं कर सकूं, लेकिन it might take me maybe 100 years before I can reach the posterior. So I have to search properly. Okay, so this is the reason that I have to include the Markov chain here. So yeah, so you must be all of you must be very clear on this point. Okay, why we don't calculate the integral? why Monte Carlo purely is not good for us, and what do you mean by sampling from the posterior. ठीक है, ये concepts आपके clear होने चाहिए. So just 1 minute. Okay, so now we come to the main part. Okay, with MC, so we have a Markov chain, and I've already showed you what that is. We draw samples from a simple proposal distribution, which is actually the prior distribution which you specify. ठीक है, so इसको आप इस तरह envision करें कि I make a proposal, जैसे in Urdu we can say ijab और कबूल. ठीक है, कि I make an offer and the algorithm will either accept it or reject it. कि I am standing at a particular point in a search space. Okay, I want to estimate the true value of the posterior distribution. I want to estimate the posterior. ठीक है, so I'm standing at a particular point. That means कि I know the probability density of the posterior at one particular point, which the initial point is the random point. So मैंने randomly एक point select किया, मैंने कहा कि यहाँ से मेरी posterior की search जो है start होगी. That is the thing. ठीक है, so then we have another distribution which I call the proposal distribution. ठीक है, I sample a point from the proposal distribution, which is in our case the prior, जो कि आप model में specify करते हैं. ठीक है, and then that is the ijab. I make an offer कि यार this is the point. Are you willing to move to this new point in the Markov chain? Are you willing to move to this new point? Then we have, obviously we need to have an acceptance criteria. Like for example, if someone proposes for marriage, so if the person will evaluate whether this person is fit for me or not. So there is an acceptance criteria, right? So based on the acceptance criteria, we'll say rejected or accepted. And if it is accepted, then the search will move from the initial point to the new point. ठीक है, and if it is rejected, then the search will keep on standing there. हम कहेंगे कि दूसरा पॉइंट सैंपल करके लाओ, तो मुझे तुम्हारा ऑफर कबूल नहीं है, कोई दूसरा पॉइंट सैंपल करके लाओ. ठीक है, so that is the essence, that is the core essence कि we have an offer which is the proposal distribution, and then we have also the acceptance distribution जो कि आगे आएगी. ठीक है, तो please keep this thing in mind. ठीक है, so we draw sample from a proposal distribution which is a simple का मतलब क्या होता है, कोई बताएगा? What do you mean by a simple distribution?
Sir, does it mean a normal distribution?
Yes, typically the normal distribution. But I mean, based on your knowledge, हमारे जो in the data sets of the industry, I think we can go for the normal distribution or the multivariate Gaussian. ठीक है, because unless you know कि the columns are following the Poisson distribution or whatever, so typically we go for the normal distribution. ठीक है, so that each draw depends only on the state of the previous draw. That is the condition of the Markov chain, not difficult to understand. So I am standing here, so the initial value of the parameter is x0. Okay, I make an offer, so this is the offering distribution. It makes an offer for x dash, and there's an acceptance function here which is the teacher. Basically it's a teacher, right? And it says, okay, according to my criteria you're fine, so you can transit here. So that means कि I have taken the next step towards estimating the posterior. तो मेरे पास एक पूरी chain बन रही है. The point is कि I make this chain up to a particular point, until the chain converges. ठीक है? Then I sample another chain, then I sample another chain, then I sample another chain, and I'm expecting that all the chains will converge to the same point, in the same way. That is the thing. Okay, you can imagine something like this. Okay, this is the first chain, it converges like this. Start the second chain, it converges here. The third chain, it converges. It's always going to converge. The Markov chain is always going to converge to a stationary distribution. That is the reason that we are using it for estimating the posterior, because there is a 100% guarantee that the Markov chain is always going to converge. So no matter from where you start your initial search, it does not matter. It's always going to converge to the same point. And this point is actually representing your posterior जो कि आपको चाहिए. सही है? So ijab or kabul, offer and acceptance, that is the main thing. So under certain conditions, the Markov chain will have a unique stationary distribution. So stationary means that the parameters of that distributions are going to converge. So if you have a Markov chain, let's say over a particular network, not for this problem, but any Markov chain, so there's a, okay, in order to transit from this state to this state, I have a probability. Ditto, I have a probability here. I can now go back with a probability. I can also go back here with a particular probability, blah, 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 blah. I can remain in this particular state with a probability. So a Markov chain is a probabilistic graph. ये आप ज़हन में रखें, it's a probabilistic graph, and that is why we are using the PDFs here. For example, the proposal distribution is actually the is a PDF. The acceptance formula जो कि इस्तेमाल होता है, it also uses a PDF. So these PDFs are being used because in the case of Markov chain, I have the probabilities of state transitions. So yeah, so please keep these concepts in mind very, very strongly. Okay? So I have a guarantee that Markov chain is always going to converge. Therefore, I'm going to use this formalism. Okay. In addition, not all the samples are used. So I can generate the chain here for a long time, and I can generate multiple chains. I have to do that to be sure that where am I heading. But we are not required to use all the samples because it's a sampling process, and sampling you are sampling randomly. This point जो कि आपने x bar next point sample किया, it is randomly sampled from the normal distribution in most cases. ठीक है? So therefore we need to set up an acceptance criteria for each draw based on comparing successive states with respect to a target distribution. That is the thing. With respect to a target, ये अब दूसरी distribution आ गई कि जो आपका acceptance function है, that is basically following the whims of a target distribution. So you have to, this is the likelihood function जो कि आप specify करते हैं. So this is the prior function which you specify, and this target is actually the likelihood function which you specify in your samples, in your code, जो कि हमने पिछली बार देखा. I hope कि some of you have gone through the code, क्योंकि इस तरह जो है ना, चले मैं assignment दे दूंगा, तो you will thoroughly आपका वो exam उस पे हो जाएगा, ठीक है? So is this thing clear? The concepts need to be very clear. I can only go to the next state if A says कि okay. A कहाँ से बोलेगा okay? Because A is following the target distribution which you have provided. Again, मैं आपको फिर बता दूं कि it might be wrong. In the first case, it might be wrong. In the second try, it might be wrong. In the third try, it might be good. सही है? So you never know what is right or wrong unless you try code it and see yourself whether the convergence is true or not. ठीक है, उससे पहले आप कुछ नहीं कह सकते. बहरहाल, we have to specify two distributions. One is the prior distribution, which is called the proposal in MCMC, and the other is the target distribution, which we are basically the likelihood, जिसको हम MCMC में target distribution कहते हैं. And the acceptance function basically derives its knowledge from the target distribution. तो अब देखें ना, now try to visualize what I'm saying. I'm saying that the Markov chain is always going to converge. Point number one, बिल्कुल सही है. Therefore, I can use the concept of Markov chain along with Monte Carlo sampling, obviously, क्योंकि sampling के बगैर तो मैं आगे बढ़ ही नहीं सकता. So I'm going to use the concept of Markov chain because I believe that it can converge to the posterior distribution. ठीक है जी, it can converge to the posterior. आप किस तरह करें भाई मैं तो सर्च तो मैं रैंडमली स्टार्ट कर रहा हूँ. ठीक है भाई, मैं आपको दो फंक्शन देता हूँ. इजाब कबूल के लिए मैं आपको दो फंक्शन देता हूँ. One is the proposal function, which we call the prior. The other is the target function, likelihood function. So जिसकी base पे I'm going to set up an acceptance criteria. And there is also a third distribution, the uniform distribution, which is just used in the formula for the acceptance. So uniform distribution is, we're using the distributions so that any sort of bias will be removed. तो आप ये नहीं कह सकते कि, you can never say कि the Monte Carlo search is going to generate a biased answer. That is impossible because you are sampling, and you are, in this case, you are taking data from three different distributions: the prior, the likelihood, and the uniform distribution. So there is no way that it can be biased. Also and you're following the Bayesian formula, which has been well recognized, and you're following an acceptance criteria which is based on the probabilistic analysis. So there's no way that it can be biased. Okay, So now keep this G.
I don't understand what the uniform distribution has to do with this.
Yes, it is just coming in after a few slides. It comes at the end. वो सिर्फ acceptance criteria का जो formula है ना, उसमें बस एक sample करके comparison के लिए इस्तेमाल होता है. We'll see how that happens. ठीक है, वो I have not specified that because that comes in the algorithm, but it's a very minor contribution. You don't need to worry about that. The main thing is to remember likelihood and the prior and the whole process. ठीक है. So this will ensure that the stationary distribution is the posterior distribution of interest. So you need to get the concept in mind. Start the search from anywhere else, any place, does not matter. It's always going to converge to one particular location, and that location will represent the whole PDF of the posterior distribution. Okay? So why that happens? That is because of two inherent characteristics of the Markov chain, which we are going to discuss very soon. वो बात की बात है. अभी आप superficial level के ऊपर एक concept बस याद रखें कि इजाब और कबूल. There is an offering function, the proposal, and there is an acceptance function which derives its knowledge from a target distribution. So let's move on. Okay, the nice thing is that the target only needs to be proportional to the posterior distribution. So we know that, for example, the posterior is proportional to likelihood multiplied by the prior. We know this, right? This is what the Bayesian formula is. So therefore, I have the likelihood, which means we don't need to evaluate the potentially intractable marginal likelihood, which is just a normalizing constant. So because of this thing, basically this thing, because prior knowledge is just, a sort of a check on what we are doing. So I'm saying because of this, I can ignore the marginal likelihood or the evidence. Okay? So we can find the target distribution easily since posterior equals to likelihood into prior. So likelihood into prior, we are giving these functions, and based, that is why we are saying that मैंने आपको पिछली slide में ये समझाया कि you have to specify the likelihood and the prior, and उनकी multiplication और MC algorithm के parameters की base के ऊपर you can sample from the posterior, directly from the posterior. You are not actually computing the posterior, but you are sampling from the posterior distribution. The sampling from the posterior distribution, that is the main thing. So based on samples derived from likelihood and the prior, yani proposal function and the acceptance function, you are basically sampling from the posterior distribution. Please keep that in mind. Okay? After some time, the Markov chain of accepted draws. इसका क्या मतलब accepted draws? कौन बताएगा मुझे? What is a draw?
The samples taken which meet the acceptance criteria.
Yeah, which meet the acceptance criteria. Draw का क्या मतलब है? What is a draw?
So it's a sampling.
The proposal, उसको आप इसके words में कहते हैं proposal, जो आपने sample करके proposal दिया है next point का. The proposal of the next point, that is called the draw. ठीक है? Will definitely converge to the stationary distribution, and we can use those samples as draws from the posterior distribution. Achha, the point is that if I'm drawing the chain like this, okay, I was here, accepted this point, blah, 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 the chain goes on. Let's say the length of the chain goes up to all the way up to this point. So this is the one of the chains that I sampled. Okay, now इसका एक disadvantage ये है Metropolis Hastings algorithm का कि these samples are actually correlated with each other. So you are saying, okay, why is that bad? You can't say that that's a bad thing, but that could lead to some sort of a bias. If the samples are very highly correlated with each other, they might be, biasing the search towards themselves. So yeah, so we have some tricks to avoid that. We'll see those later. And find the functions of the posterior distribution in the same way as that for the Vanillo Monte Carlo integration. So that is basically a very general statement, but you just have to understand the basic concept जो कि मैंने बता दिया, ठीक है? Now we come to this actual algorithm, which is not easy to understand. You just have to pay a bit of attention. So many people. Only 6 people are here. Okay, the purpose of MH algorithm. Yeah, by the way, I think Hastings. I forgot. I think these are the. This is the name of a guy. I forgot about Metropolis. Whatever. The purpose of this MH algorithm is to generate a collection of states. That's what we want, according to a desired distribution Px, which is in our case the likelihood function. Or you can say this is the posterior. In fact, अभी आप likelihood की बात ना करें, वो हमारा likelihood and prior are our internal problems. They are our internal functions. तो अभी हम generic बात करें. So let's say कि we at the conceptual level we say that this is the posterior. So you can say कि why you're talking about the posterior right now? We are going to estimate that. I'm talking about that because I'm sure that the Markov chain will converge to the posterior distribution. Therefore, I'm saying in advance कि हम उसका estimate करें. That's the thing. To accomplish this, we use a Markov process. Obviously, we use it, which asymptotically, obviously, sampling may, there's no discrete 1 or 0. There's always a convergence towards some value, right? So that's why we use the term asymptotically. Reaches a unique stationary distribution pi of x, such that pi of x equals to p of x. That's what I told you in the last slide. Okay, I am already saying that in advance. Okay, the distribution to which the Markov chain will converge will be the posterior distribution. Okay. A Markov process is uniquely defined by its transition probabilities. Obviously, that's true. X dash, though, you can envision the discussion will go like this. So I have x here, and I have x bar here. So the discussion will go like this. Okay? So I want to estimate the probability of x bar given the previous state. That's the main thing. Okay. And for this, I am doing all this, the proposal function and the target and the acceptance, vagara, vagara. It has a unique stationary distribution pi of x when. Now these are the criteria of the Markov chain. Only you can do that when these two conditions are satisfied. In the first case, there must exist a stationary distribution. अच्छा यार ये कैसे guarantee करें? Why is the Markov chain guaranteeing that this stationary distribution exists? How can it guarantee? We'll see that. The distribution must be unique. If you are able to satisfy these two values, these two conditions, then it means that I can use the Markov chain to estimate the posterior distribution. Okay. Now how this happens, let's see. मैं आपको थोड़ा सा आसान अल्फाज में समझाऊंगा. ठीक है. The point number 1 is कि हमने कहा कि यार stationary distribution exist करनी चाहिए. There must be a stationary distribution. So that condition is achieved through a concept which is called detailed balance. Detailed balance का मतलब क्या है? कि this transition is reversible. That means the probability of going from x to x dash is the same as the probability of going from x dash to x. That is called a reversible transaction, or a reversible, transition. And this condition absolutely ensures that a distribution will always exist. So if you want to write that down in words, in a formula, it goes on like this. Okay, probability of x bar, x dash given x into pi of x equals to probability of x given x dash into pi of x dash. That is the Bayesian formulation of this. Okay, these two probabilities are similar to each other. Okay, either I go from x to x bar or I go from x bar to x. The probabilities at that point are going to be similar to each other. Pi of x is actually giving the probability of the posterior distribution at this, for this condition. Okay, I'm going x to x bar x. I'm going from x to x dash. So what does the Markov chain say at that point? That is pi of x. And I'm going from x bar to x. And what does the Markov chain say at that point? That is pi of x dash. सही है. तो actually we are assuming कि pi equals to p. लेकिन ये आपको सिर्फ समझाने के लिए ये फॉर्मूला लिखा गया है कि that is what you mean by reversible transition. कि going from A to B is equally likely as coming back from B to A. Going from A to B and coming back to A from B, A to B, B to A. The probability is the same. So that is the first condition that must be present for me to ensure that I can sample the posterior from the MCMC or the Markov chain. Okay, so is this thing clear?
Sir, this is the uniform distribution.
नहीं अभी देखिए, we are not specifying कि distribution कौन सी है. Right now we are just at the superficial level describing the concepts. We are going to be tackling the distributions when we go to the code. As far as the uniform distribution is concerned, जो कि Metropolis के अंदर है, वो अभी आया नहीं है. सही है. I'm just discussing the concept right now. Just understand the concept. कि the condition of detailed balance will ensure, absolutely ensure, that there will exist a stationary distribution. Okay, this reversibility ensures that the distribution exists. कि वो एक distribution exist करती है जो converge कर जाएगी because of this condition. अब उसका mathematical proof क्या है? We absolutely don't have the time to see that, but just remember it at this level. ठीक है? This is the Bayesian formulation of this particular phenomenon. This is just the Bayesian formulation. हमने तो ये कहा है कि pi, what the Monte Carlo Markov chain estimates is equal to the posterior. We say that they are the same things. So here I can obviously replace pi with, I can replace pi of x with what? G. कौन बताएगा भाई? If pi equals to p, I can replace pi of x with? हाँ जी बोले भाई.
ऐसी बात है सर.
हाँ, p of x. So pi तो सिर्फ इसलिए लिखा हुआ है ताकि आपको superficially समझा दिया जाए कि this is the distribution which I want to estimate, and this is the distribution which is the chain is estimating. For us, they are the same things. It is just to given आपको concept explain करने के लिए ये बात लिखी गई है in the Bayesian formulation. ठीक है? So the reversibility of the whole process is going to guarantee that a distribution exists which is going to be stationary, which is going to converge. अच्छा, दूसरा point हमारा क्या था कि that distribution must be unique. Now this again is guaranteed through some properties of the Markov chain. वो कौन सी हैं? उसको हम कहते हैं ergodicity. I don't know, ergodicity, I don't know about that. Okay. So what does that mean? Requires that every state must be aperiodic, that the system does not return to the same state at fixed intervals. Obviously, this is a bias situation, right? Okay, in a game also you can discuss someone is cheating if this sort of situation happens. If you are getting something with a certain probability after a particular amount of time, that means that is possibly a fraud. सही है कि not like कि जो आपको pays मिलती हैं, but in a normal transaction कि you are displaying a fixed behavior which goes against the logic of the whole process. So in our case, we want the search to go ahead. हम चाह रहे हैं search आगे बढ़े, लेकिन if the search is returning to the same state after a fixed number of intervals, then that means that something is not right. Okay? So therefore that means that the search is periodic. I don't want the search to be periodic, otherwise मैं आगे किस तरह जाऊंगा? तो इसमें क्या बनेगा? Like for example, if I'm transiting like this, and then after 2 or 3 intervals I go back here. After say let's say 50 iterations मैं वापस state पे आ गया. सही है? And then I start the search from here. Let's say I take another color. I start the search from here again. And let's say after 50, then I go here. And after 50 iterations, let's say I come back to this state. It's just a hypothetical scenario. So ये क्या? ये तो periodic हो रहा है ना? So therefore it has to be aperiodic. It can't go like this. So this chain इसको ensure कर देती है. Every state must be positive recurrent. ये दूसरी condition and the final one. That means the expected number of steps for returning to the same state is finite. So I can return to the same state, but I don't want to return to that same state periodically. Through a random search, I can. For example, let me just draw this search for you. Let's say I was here, and then I just keep on going like this. Okay. So now at this point of time, I just returned here. Just because the acceptance criteria took me there. The acceptance criteria, there is no cycle to it, right? It is not a periodic thing. हर 10 steps के बाद आपने वापस वहां आना है. That's the thing that we want to avoid. That is avoided. Otherwise, you can't guarantee the condition. Okay. So so I just now I take the next step from here. Okay, I just reached here. So I was here. So let's say and then after this, I just reached, let's say, वापस, I just reached here. So it is possible for me to go back to a particular state, but it does not have to be periodic. And if you are going back after an acceptance criteria, then it has to be in a particular number of time steps, finite steps. ये ऐसा नहीं है कि 3 लाख iterations गुजरेंगी तो फिर मैं state पे आ सकता हूँ. तो आप समझ रहे हैं कि I have to maintain a balance. I'm not forbidding coming back to a state, because that can happen in a search. We are actually sampling randomly. Therefore, we can come back. It is possible for the search to go back. Just I showed you the graph for the random walk. So it's possible to come back, but we have to ensure that this is not periodic. And if you are coming back, then you are coming back in a finite number of steps. That is what you want to keep in mind. Okay. सही है? Is this thing clear? जी मरहबा, नए साथियों को मरहबा. आप जरा ध्यान से सुन लीजिएगा क्योंकि लेक्चर बहुत जरूरी चल रहा है. ठीक है, तो is this thing clear? So for me to use the Markov chain needs to follow 2 characteristics. First of all, it needs to guarantee that the stationary distribution must exist. So for that to happen, I have this condition of detailed balance. In the case of detailed balance, it means that this transition is reversible. And that is basically being displayed by this formula, which I've explained very thoroughly. And then obviously I need to ensure that the distribution is unique. आप समझ रहे हैं ना? अब आप खुद just try to envision के because of this aperiodicity and this positive recurrence, this will be unique, because I'm forbidding the cycles, fixed cycles के after 10 steps come back, after 10 steps come back. I'm not doing that, right? So it's an aperiodic situation. I'm allowed to come back, but in a finite number of steps in a random way. So that definitely ensures the uniqueness of the whole scenario. So this basically satisfies our 2 conditions के जो Metropolis Hastings की हैं कि you must satisfy for the algorithm to work. So now let's proceed. So MH algorithm involves designing a Markov process. Now you know that by constructing transition probabilities, right, that fulfills these 2 conditions such that pi x is chosen to be px. Now this is the problem statement that you need to keep in mind for your quizzes and hourlies, blah blah blah, etc. So yeah, this is, I have explained this. Because if you don't understand this, then there's no you can't go ahead. Okay, ये मुश्किल है थोड़ा सा समझना ना. So this is the main concept. Now, अच्छा, this is the formula that we wrote. That is the detailed balance that we need to achieve. ठीक है. अच्छा, इसमें ये भी मैं आपको बता दूं कि the prior and the likelihood that you specify, at least the prior is supposed to be symmetric. Okay, but in case you say I can't guarantee this the symmetric distribution, the normal distribution might be symmetric, but maybe you have a distribution which is not symmetric, and you specify that as the prior. ठीक है, हो सकता है, कोई मसला नहीं है. So हम in that case we set up the acceptance criteria to cater for this. Otherwise, the acceptance criteria is pretty simple. If your prior is symmetric, if your prior is asymmetric, then you have to be a bit more intelligent to specify the acceptance criteria. So मैं जो आपको acceptance criteria दिखाऊंगा, I'm going to show you the one which is the best one, and that is the one which is being normally used. I don't know कि pi MC3 या pi MC4 में इस वक्त कौन सा इस्तेमाल हो रहा है, I don't know, but we are going to be seeing the raw code for that basically. ठीक है, right? So I told you that pi is p, so I just replace that by p. It's the same thing, and when I put that in, I can write this notation like this as well. It's just a ratio. I told you that because of the ratio, I am able to eliminate the need for calculating the marginal likelihood. ये भी point आप याद रखिएगा, ठीक है? So I already told you this. Okay, the approach is to separate the transition in two steps. So I am at step state 0, and here sorry, not this. So I have the proposal distribution, which is the prior. In fact, it proposes a new state, and here is the teacher, which is the acceptor. Okay, and it says yeah, okay, you can just go here. So this going here is defined by A, the teacher. So that is basically a proposal and an acceptance. ये इजाब कबूल है, ठीक है? So you propose something, and if the A accepts it, then you can transit to the next state. That's the thing. The proposal distribution G, we can call it G, for example, is the conditional probability of proposing X dash given X, and the acceptance distribution is the probability of accepting X. So just remember this, कि ये मैं आपको already बता चुका हूँ कि both the proposal and the acceptance are probability density functions. ठीक है? So अब now I can write it like this. This is the important formula that you need to keep in mind for your hourlies or your quizzes. Probability of X dash given X. If what is my probability of moving to the next state? यार मैं आपको बताता हूँ. That is equal to the probability of the value proposed by the proposal function given your current state. Obviously, that is the condition for the Markov, right? Given your current state, multiplied by the acceptance. So if both these things are independent of each other, right? This is an independent function, and this is an independent function. So I'm able to multiply these two probabilities to get the probability of P of X dash given X. And remember, I told you G of X dash given X derives from the prior, and A of X dash comma X derives from the likelihood function, जो कि आप specify करते हैं. That is the main thing. We're going to see that in code right now. So this formula should be very easy to understand for all the people now. ठीक है? कि when will I go to the next state is defined by obviously what I am proposing, multiplied by whether I'm accepting or not, and both of these are probabilities. Achha, I can write this formalism like this. I mean, I can use this one. Okay, just let me wait. Okay, I can use this in this to derive this. Okay, अभी इतना time नहीं है कि उसको हम तफसीली देखें, but you can basically understand what's happening here. So A of X dash comma X over this equals to P of X dash G of X given this dash. So this is obviously here, ये इधर आ जाएगा, तो that's the Bayesian formulation. सही है? So this is the thing that we're going to use, the acceptance criteria. We are going to using P, and we're going to be using G. Remember that P is something which is very close to the posterior distribution. So we're iski detail hum dekhte hain. I'm talking about the likelihood actually. So I just wrote these same formulas here. So this is the detailed balance. I just replaced pi with P. I put that in this ratio form. This is the main thing that you need to keep in mind and explain. And then obviously I can write this in this form. So this is just the repetition. And this is also the repetition. I just wrote that. The next step in the derivation is to choose an acceptance ratio. Now is to choose an acceptance ratio that fulfills the above condition. And one common choice is the Metropolis choice. Metropolis choice kya hai ke this calculation is basically give you a probability, and I have to find out the minimum of that. So the minimum of that is obviously this cannot go more than 1. So the minimum is always going to be this one. for the acceptance ratio. So this is the ratio. This is not the acceptance criteria. Yusuf, मैं आपको वो ये specifically बता रहा हूँ. Right now we are estimating an acceptance ratio, जिसको we also use the symbol rho to basically model that. ठीक है, to define that. Based on the acceptance ratio, I will define the acceptance criteria in which I'm going to use the uniform distribution. The acceptance criteria will tell me whether you should go to X dash or not. So X to X dash, that will be defined by the acceptance criteria. But first, for the acceptance criteria, I have to first calculate the acceptance ratio. Acceptance ratio is calculated based on the given P and G's. P and G's. ठीक है, वो तो कंपनी का नाम आ गया. So this is the Metropolis choice. And whether you estimate AX dash comma X or AX comma X dash, so it's a reversible thing. So it's the same thing. ठीक है. So so you can estimate either one of them. ठीक है. So now let's see how this happens. So just keep this in mind. The acceptance criteria is always going to find out the minimum of that. I think this basically means that due to the sampling process, it could be possible that this ratio exceeds 1. In that case, we have to just limit that to 1. Okay, because it's a probability, you can't. For me, the acceptance ratio always need to have a maximum value of 1. That is what we are proposing here. Okay? This is not a acceptance ratio, is not a probability. Acceptance ratio is just a ratio which is calculated in this way. But we are imposing a limit on that. So the top limit for the acceptance ratio is 1. That is what the formula says. Please keep this in mind. Okay. And now we finally come to this, the algorithm. So this is now you pick an initial state. That means you pick the first point from the posterior distribution. So pick the first point from the posterior distribution. Okay, this is the point. So this is a sample from the posterior distribution, which I have defined randomly. Obviously, set t equals to 0. That's my first timestamp. Now iterate. Generate a random candidate X dash according to the proposal distribution. Now, how you can just, if this is the normal distribution, you can just sample based on the parameters of that distribution. You have defined the normal distribution initially, so just sample a number from that. Okay, yeah, or you can sample from the prior. Calculate the acceptance probability, which is this is the probability. So I was wrong in the previous step. So this, the probability is a ratio. We're putting a limit on that. So uska phir sawal ye ke maybe under certain condition this goes more than 1. So we are just restraining that to a probability. I don't know how that will happen, but it is possible to happen because we are sampling, and it is possible that sampling can go in some place where that happens. So we are just limiting that. The maximum can be 1. Okay. So the acceptance probability is this one, and now we have the acceptance criteria. Okay. So now here we are using the uniform distribution. So basically, in this case, I am using 3 distributions: P, G, and U. So I generate a uniform random number between 0 and 1. Okay, and I accept the new state if U is less than the acceptance probability. Basically, I have done this condition because I'm sampling between 0 and 1, so that the comparison here can become easy. So if the sample number is less than or equal to the acceptance criteria, acceptance probability, then I accept the new state. And if it is greater than that, then I reject the new state and just copy the old state forward. So I remain there. So it is possible that I am here at t equals to 0. I go to a new state at t equals to 1. And this is t equals to 1. And it is possible that the proposal was rejected. So at t equals 2, I'm in the same state. So this is the acceptance criteria, after which ये बहुत simple आपको लिखा हुआ है. So this will help you explain how things are happening. So now you understand the perspective behind all of these things. So I can ask you in the hourly the concepts behind the Metropolis Hastings algorithm. What is the concept behind G? What is the concept behind this ratio? I can ask such questions. Okay? So can you in any way think why this condition should lead to an acceptance and why this condition should lead to a rejection? Now that is the question. Okay, I want you to generate a Markov chain and reach here, which is my estimate of the posterior. I have an acceptance criteria. No matter what you do here, where you go or jis taraf ja rahe hain, I'm going to guide you through this. So how am I guiding? What is happening basically? So I am basically forcing the search to remain in those areas in which P has a higher density. So let me write that down. I am forcing the search, or the, you can say the transitions, to occur in such a way so that the search remains in areas where P of X is high. How will I know that? Because I know that because I have the likelihood function. The likelihood function and the prior function are giving me some idea of the true posterior. And based on these two functions that you have given, I am somehow able to force the search to remain in those areas in which the proportionality of the likelihood and prior is high. समझ में आ रही मेरी बात की? So posterior is equal to, or approximately, sorry about that, not equal to, is approximately equals to likelihood into prior. So I am given these two functions for two in the search, and based on the the cross product of the probabilities, or the probabilities from these two functions, I am able to basically force this condition. बस ये बात आप याद रखें कि the two functions that you have specified, their product, their product, the distribution from that product is sampled. Okay, it's sampled from a distribution, but their product basically can guarantee you that the search is going to remain concentrated in those areas which are highly probabilistic with respect to Px. So for example, this can be the whole room in which you are searching. Okay, and let's assume that this is the area which is where Px is very high, and this is the area where Px is low. So that your state transitions are basically going to remain here in this area. How that happens? Because of this acceptance criteria. So this concept should be super clear in your mind, super clear. How this search is proceeding. Yes, it's super clear in your mind. The fact that you are sampling a random number and you are saying that if this random number is less than A, because in the acceptance criteria, it is actually a probability of occurrence of something. So I'm saying if this occurrence is high, U bhi usse kam hai, so then that means that I'm okay. I'm near to the previous one. I'm near to high density area. Jaane do. But if अगर आपने U sample किया, you sampled U randomly, सही है, वैसे ही जो 0 to 1 पे random sample और वो फिर भी A से बड़ा है, then that means के you are not in an area जहाँ पर P की value जो है ना वो highly probability, it does not have a high probability in that area, therefore you are rejected, try something else. सही है? So that is the basic functioning of the algorithm, so you must be able to understand that. So now we are just some logistic information here, provided that specified conditions are met. So the empirical distribution of the sequence of saved states. So we are saving the states here. Ab saved states ko save karte hain. Will approach the posterior. They will be samples from the posterior distribution. That is a guarantee because of the condition of uniqueness, and because of the condition there are no क्या कहते हैं, कौन सी दो conditions? Because of those two conditions, these ones basically, detailed balance, aperiodicity, and positive recurrence. So this thing happens because of detailed balance, aperiodicity, and positive recurrence. ये आपका हो जाएगा. You must keep in mind that you do not know G of X bar given X in advance. And also you do not know the number of iterations necessary for proper estimation. You also do not know from where to start. So you give a random sampling point. The search will behave very strangely based on this random sampling. Okay? Both are free parameters of the method which must be adjusted to the particular problem in hand. Now, this is the intuition which I've already explained to you in the last slide. We accept the state, a new state, only when the density of P at X dash is more than the density of P at X. That is ensured by the acceptance criteria. So we always move towards areas where P is dense. I mean, it's sort of a bias, but that's how you want to proceed, right? I mean, if you are given the likelihood in the prior, you will want to remain in that area where uska jo product hai wo zyada highly probable ho. So that's what you are doing here. आप ये कह सकते हैं कि ये because I'm doing sort of a bias thing here, so you can get stuck in some local optima, in some local maxima. You're trying to maximize the posterior, right? So you're finding the map maximum a posteriority, right? Okay, what is the point at which the posterior distribution has the maximum value? You अक्सर ये निकालते हैं, लेकिन उससे पहले we have to estimate the posterior. So currently we are estimating the posterior. So to avoid being stuck in local maxima, because तो कोई बताएगा कि why will we stuck here? The idea is that if you are forcing the search to remain in one area, then you can get stuck in a local maxima. Okay? So we accept occasional moves to lower density regions to remove this bias. Occasional moves to lower density regions. It turns out that the correct probability of doing so is given by the acceptance ratio. So the acceptance ratio is the probability of basically is the probability of is doing an occasional move to an area of lower region so that I don't get stuck in local maxima. Yeah. The acceptance criteria only looks at the ratios of the target distribution. So the denominator cancels out and does not matter. That is the thing. So we are only looking at the ratios. That is why we only need samples from a distribution proportional to the posterior distribution. So this is the reason that because of the fact that we can ignore the denominator से हम जान अपनी छुड़ा सकते हैं. So we are able to sample directly from the posterior. Otherwise, I've told you what the problem with the denominator is. We don't have an idea of all the possible values which the posterior can take, so that I can sum up over them. We don't have those values. उसके ऊपर हम integrate कर नहीं सकते. You can say कि we don't have an idea of the parameters of all the parameters of the model over which I can integrate to find out P of X. I don't know कि वो P of X किन parameters के through आ सकता है. So therefore, it's not possible to calculate that. And search will be expected to bounce around in such a way that it spends its time in places proportional to the density of the posterior distribution. In other words, it is sampled from the posterior. So you can imagine, sorry about that, yeah, you can imagine the search as like this. So the search can go like this, sometimes going like this, sometimes going like this, and then converging here. Okay, then you can have another search like this, sometimes going like this, could be spikes here, and then converging here. And similarly, you can have a third. So you are doing this. Achha, different implementations of MH will be behaving differently. So again, I don't know the latest implementation. I'm just teaching you the basic concept. That's my job here. So it converges here. Now the whole story is that we want to use this. We want to use the MCMC algorithms. MH is one of the older algorithms, right? Currently we have the new algorithm which is called NUTS, which is being used by PyMC3. लेकिन मैं वो पढ़ाऊंगा नहीं आपको. वो आपका काम है. मैं आपको बेसिक चीज पढ़ा रहा हूँ जो बुनियाद है. ठीक है, इतना टाइम नहीं है. तो we are using NUTS basically. और उसमें we are going to discussing tomorrow. उसमें use होता है hierarchical sampling का concept है, which is becoming very famous now. And hierarchical sampling is being provided in PyMC3 now. But we are using NUTS. So the main point is that we want to use these algorithms to actually find out the predictions. That is the main thing. Okay? So now this is the whole concept here. अच्छा, different options for the proposal distribution. So independent sampler. This is one thing जो कि मैंने आपको अभी नहीं पढ़ाई है. Gaussian, which is what we normally take. We can also have a random walk. We can define the proposal to generate a random walk. So the random walk क्या करती है? Takes a random step centered at the current x, and efficiency is a trade-off between the small step size with high probability of acceptance and a large step size with low probability of acceptance. ठीक है? So random walk क्या है? Like I told you in the previous, like I showed you here. Sorry about that. Yeah, I showed you here. Okay, this. I don't jump that much here. The jump. Sorry, just change the color. Yeah. So the jump here in the orange curve is very small. So I know that I will not jump much because I want to jump a very small amount because I know कि उसके accept होने का chance ज़्यादा है. I'm going in that direction, fine. But sometimes I jump highly because I have to, जैसे हमने explain किया है. So in that case, the acceptance will be less. So therefore, the probability of this jumping, these spikes, is very low or low as compared to the probability of jumping very small. That is how the search is proceeding. So you need to keep this thing in mind. Okay, that is how the search is proceeding. Okay, small jumps are more probabilistic than higher jumps. Sometimes you need to do the higher jumps. That is the thing that you need to keep in mind. Okay. So note that the random walk may take a long time to traverse narrow regions of the probability distribution, which is obvious. जी
सर, आपकी आवाज बिल्कुल गायब हो गई थी पिछले.
अभी आ रही है?
सर अब आ रही है बेहतर, लेकिन जब आप डायग्राम बना रहे थे तो एकदम से पॉज हो गई थी आवाज.
Okay, let me do that again. So I told you कि all of you understand this, right? You do understand this? जी do you understand why the spike is coming, all of you?
सर, आपकी आवाज फॉर सम रीजन बीच बीच में से कट रही है. आई डोंट नो इफ इट्स जस्ट माय इंटरनेट कनेक्शन या फिर सबको ये महसूस हो रहा है.
So all of you know कि why this spike is coming?
नहीं सर, वो उसी वक्त पे जो है एक्चुअली
ये तो
आवाज
अभी
कट
मैंने
ऑफ हो
एक्सप्लेन
गई
किया था
थी.
कि but I told you कि if I am biased, I don't jump that much to go to the next state because I am sure that my offer is going to be accepted if I remain in an area of higher probability. But we have seen that this might actually lead to a bias. I will go to a local optima. To come out of that, I sometimes also go to a region of low density. ये बात तो clear है ना?
Yes sir.
So this is what I'm doing. This is the thing that I'm doing. I'm jumping a lot to avoid any local minima. But the point is that I am jumping not that much frequently. Here I am doing these jumps, but these jumps are not frequent as compared to the small jumps here. You see, these are the small jumps. This is the long jump. These are the small jumps. This is the long jump. So why am I doing the long jump? To avoid the local minima. To avoid the local minima. I'm doing the long jumps to avoid the local minima. Okay? But the point is that their probability is very, very less as compared to the probability of small jumps. Because I just, मैं कह रहा हूँ कि यार मुझे रहने तो यहाँ पे. If you think I'm going to stumble into some local minima, ठीक है, you can push me sometimes to the other room, but then I'm going to come back here and I'm going to start searching here. Then you can push me to the other room again after like 10 minutes or 15 minutes. But after the next step, I'm still going to come back here and do, just to ensure that I don't do anything wrong. Okay, I don't get stuck in something wrong. It's like similar to having. Ji.
Sir, this step avoids both local maxima and local minima. right?
Yeah, bilkul. This is whatever you're doing. In this case, I think we are finding out the minimum value in the acceptance ratio. It could be the local minima, but it avoids any type of both of these scenarios. Okay, सही है? So
Yes.
Yes, sir.
efficiency is a trade-off. अब trade-off किस तरह करना है? अभी trade-off तो आप you can do that in the experiments. कि trade-off क्या है? How is algorithm कैसे program हुआ है? That is not our headache. You just have to understand how this is working. Note that the random walk may take a long time to traverse narrow region of the probability, because if you are selecting the next step completely randomly, random walk might take a long time to traverse in areas narrow regions. Narrow regions means ke if the posterior distribution is like this. No, sorry about that. So the random walk will best estimate the posterior if it is very ideal. Let's say a Gaussian curve. But if the posterior is like this is a narrow area. So random walk might have difficulty, because if it makes a long jump here, so it might end up here. So it might not be able to estimate this shape. That's what we have to estimate, right? We have to estimate the shape of the PDF. We have to estimate the values here and then find out the shape from those values. That's what we are doing from the MCMC. Okay. So मैं कहना ही चाह रहा हूँ कि if there is a narrow region in the PDF curve of the posterior distribution, the random walk might take a long time to converge to that because of the fact that it is jumping about randomly. That's the thing. So changing the step size so that a target proportion of proposals are accepted is known as tuning. No, ये वो चीज है जो आपके हाथ के अंदर है. So you have the parameters of the whole process. You have the likelihood function, you have the prior function with you, and now आपकी responsibility ये है कि आपने उसको करके you have to basically estimate the posterior. So just finishing up with the disadvantages, and then I will show you the hands-on. It's almost 10 o'clock. This I told you, the samples are not completely uncorrelated, so the samples are correlated. In the long term, they will follow the posterior distribution, so I don't need to worry. But still, if I have this chain, so here I am using the different states here, so I have the different states. So a set of nearby samples, that means let's say that these samples will not correctly reflect the posterior distribution. ये problem है सारा ना, कि आप कह तो रहे हैं हाँ यार, after 10,000 iterations I'm going to converge to the posterior distribution. Clap, बहुत अच्छा काम किया आपने. But the point is कि I have to estimate the curve for that, right? And I estimate the curve for that based on every value that I have sampled, every state value. Okay? So the reason is if the point is if I take a small region here, or a small region here, or a small region here, then in that particular region, the points might be very closely correlated with each other. That's the thing. So we need to have independence, because correlation means this might be biased. This might be biased. They are very strongly correlated, so they are very near to each other, in fact, and they might be biased. Okay? So to get a set of independent samples, throw the majority samples and only take every nth sample. So it is possible that I have this state, I accept, and even though I accept, I don't accept this, क्योंकि मेरे नजदीक क्या है कि यार ठीक है तुम अच्छे तो हो, you are accepted, but the point is कि you are correlated to me and I don't want that. I want someone who's not correlated to me, or जिसके साथ मेरी correlation बहुत कम हो, and then this is okay for me. So that's what it is. Okay, take the nth sample. So you can say from every 3 points which are accepted, I just accept one of them for some value of n, which is determined by examining the autocorrelation. So that's what I can do. I sample. If I accept a new state, I see the correlation. Then I sample a new state, I see the correlation. I see the correlation. One of those which are इनमें से जो सबसे कम correlated है, I can take that and move ahead from that. That is what I have to do. Again, I do not know how this thing is being implemented in the current APIs, but this is something which is done basically to avoid this autocorrelation scenario. Okay. So autocorrelation can be reduced by increase. एक तो solution ये जो मैंने आपको बताया, you sample multiple points and take the one which is more the least correlated with the previous point. The other is to increasing the jumping width. Okay, you jump more, like we are jumping for the to avoid the maximum local maxima. So you jump into the area of low density region, but this will obviously increase the likelihood of rejection as well. Now, again, there's a trade-off. कि jump कितना करना है वो आपको पता नहीं है, सही है. So we have to see the algorithms कि which of them are providing us this this functionality for experimenting with the jumping width. We'll have to see. Too large or too small a jumping size will lead to a slow mixing Markov chain. Too large or too small a jumping size will lead to a slow mixing. Too large, I might go into low density, very far away. Too small, and I might have something which is very, very similar. There's no, मुझे उसकी ज़रूरत नहीं है, ठीक है? Slow mixing Markov chain. A highly correlated set of samples, so that a very large number of samples will be needed to get a reasonable estimate of any desired property or distribution. If you have these two problems, then you will need to sample for 100,000s of iterations before you can converge to the posterior distribution. That is the disadvantage of these Bayesian methods. We can't do anything about that. Okay? The initial samples may follow a very different distribution. I told you this at the beginning of the class. Okay, the initial samples are just trying to find their way about the whole search space. So their results are not reliable. So if you say, okay, I want to take every chain from the start, then you are wrong. You need to give a burn-in period. So yeah, especially if the starting point is in a region of low density. That can happen. So you start from an area of low density because you're starting from a random position. लेकिन आपने जो random position दी है, you do not know whether that is an area of high density with respect to the likelihood and prior जो कि आपने specify किया. Because we are going to be estimating the posterior based on the likelihood and prior. तो आपने जो initial point दिया है, maybe that is far away from that probability density. Therefore, you might be starting in a low density region, and if you don't jump much, then you're always going to be remaining there, and you're not going to converge until you start from another point. सही है? So इसमें हम कहते हैं burn-in period is typically necessary where an initial number of samples, the first 1,000 or so, are thrown away. So अब ये really implementation मैं आप लोगों पे छोड़ूंगा. I'm going to show you the hands-on in a while, but it is your job to find out all the intrinsic details of the APIs and the parameters, etc., based on whatever I've taught you. आपको उसका जरूरी है. अच्छा, I think okay, I have uploaded the files. You're supposed to first open this MH file. I have uploaded MC2 and PYMC1. I'm working on this, so probably मैं आपको कल दे दूंगा. इसमें बड़ा interesting problem है, which is solved by this Metropolis Hastings and its extensions. PyMC1 को भी execute ना कीजिएगा. It's giving some, it's taking time to execute, probably because of some issues. ये चल रहा है अभी सिलसिला. It's getting stuck here. बहरहाल, let's first go through this. Okay, so we just have this import OS and this all these libraries. This is the future in which I import the division. So this means that actually you have to implement the division operator. I just forgot about that. Yeah, इसमें था कि I think you have to execute division on the division sign, something like that. Only division. The other things, so
Sir,
we are not G.
What does the precision 4 mean? Percentage precision 4.
I think it's for the decimal points. 4 decimal points.
Okay, sir.
Okay. Yeah, so you can use the logging if you want. So आपकी अपनी मर्जी है अगर logging use कर जाए. Theano, actually, I will tell you that Theano is a mathematical library. So it's very famous. So some APIs are using this Theano. Theano is a Python library and optimizing compiler for manipulating and evaluating mathematical expressions, especially matrix valued ones. In Theano, computation expressed using a NumPy-esque syntax and compiled on efficient either CPU or GPU architectures. So there might be some programs which are using Theano for mathematical functions. So again, I'm not sure which are the libraries which are actually using that, but it's also used as a deep learning backend by some programmers and in some applications. Bahral. This is the typical scipy.stats module. So just let's execute that. I've already executed this, so I'll do it again. Achha, now we just implement that Metropolis Hastings algorithm by default. So I'm not calling any function here, which I can call in like when I do use this PyMC3 library. I can actually call that directly, but right now here for explanation, हमने call नहीं किया अभी. So how many times I've accepted? Sorry, n is 100k. In one go, I sample 100 points. That's the thing. H is a constant, which we'll use later on. A and B are the parameters of the beta distribution. I think we are simulating the coin toss here, similarly to how we saw that in the PyStan case. Okay. So likelihood equals to stats.binomial. Okay, and prior equals to stats.beta a comma b, where these values are specified by us as the starting point. Sigma is 0.3 to be used as the parameter of the normal distribution for sampling the proposal, for sampling the proposal. Okay? So I start with theta. Theta is the like x dash. So I start with theta equals to 0.1. That's my starting point. So again, this could be in a region of low density. This could be in a region of low density as compared to the high density region of the posterior distribution with respect to the likelihood and the prior. Okay, I run it for 10,000 iterations. Samples equals to np.zeros, number of iterations plus 1. So it's just initializing this. And the first, I have the first element as theta, because that's what I mean. This is the first element of the chain. In fact, ये जो है ये chain का पहला element है. So I just put that as theta, which I start with here randomly. आ गया theta. This one. Okay. So it's a very strange error. The rest we have specified it here. So now we start the actual algorithm. So for the actual algorithm, what happens here is for I in range naniters, obviously this is true. Theta p equals to theta plus stats.norm, this one. So this is a proposal, right? This is not the actual new value, right? I'm just theta here. I'm theta here. And here I propose theta p as a proposal, which is like the original theta plus the. अब देखिए ना इसके अंदर, this is where the dependency on the previous state is coming in. Okay, we are sampling g x bar g x dash given x. So this is where it is coming here. Okay, you are deriving the new value of theta based on the original value of theta. Okay, plus you simply sample from the normal distribution. ठीक है, तो you generate the, now here is where you use the sigma. जो आपने ऊपर specify किया था, and sigma is again in your hands. Like these are the parameters which are in your hands, right? Then you calculate rho. Rho is the acceptance probability, not the criteria. The criteria is implemented here. This is the acceptance probability. अब आप देखें कि हो क्या रहा है. Minimum of let me just clear that. So this is the whole thing that we want to keep in mind. Let me just increase this. Okay. So target, you implement the target function. आप उसको likelihood pass on the prior, pass on the 100 samples that you have made per step, pass on the value of h, and pass on theta p, which is the proposed value, divided by the again the same thing divided by theta. So that is the formula that we saw in the pseudo code basically. Now, what is this target function doing? Now, let's look at that very carefully. So it takes on these values, and we say if theta is less than 0, greater than 1, it's not, because we are sampling from a density function, right? So I just return 0. You're doing some error, right? Otherwise, in the normal case, now अब देखें क्या वो कर रहा है. Likelihood, which is primarily your binomial function in our case, based on the 100 samples per step, and theta, which is the current, which is basically in the first case. In this case, it is actually theta p. So that is the proposed estimation of the posterior, proposed based on the proposal theta p. So देखें वो कैसे estimate हो रही है. Likelihood multiplied by prior. Likelihood dot PMF, PMF, the probability mass function of the binomial function, centered at h. H is that parameter जो कि हमने किया था कि the probability of success I think is 0.61, multiplied by the prior dot PDF theta, उसका PDF, because it's a density function, right? Which is the beta distribution I showed you in the last class. It's actually the beta. It's like a normal distribution, but it can take on certain different shapes as well. So now this is the posterior estimation जो कि मैं आपको समझा रहा हूँ. Simply the multiplication of the probability values from the likelihood and the prior is going to give you an estimate of the posterior. That is it. Simply हो रहा है. अब आप कहेंगे यार ये तो बड़ा simple सा काम ये नहीं है, इस वजह से क्योंकि you are providing the theta based on a random estimate. That's the thing. उस random estimate की base के ऊपर you are estimating the value of the proposed posterior, and then you're returning that. Okay, so I first estimate that for the proposed theta, divide that by the target theta, and see what is the value, minimum 1, whatever, and then okay, I can just see here. Okay, so I just don't want to print the row here like that because it's going to generate a large number of rows. So I can just print the last value of row. What about that? Okay, so I'll just do that later on. So row is this one, and then I do the same wo jo uska tha, the code from the random distribution. So I just sample a number from the random distribution by default between 0 and 1. If u is less than row, accepted theta equals to theta p. That's it. And then obviously I have to put the new one as the sample, because even if theta is not equals to theta p, I have to put the new sample. In this timestamp, I rejected it basically, but I'm still putting the same state in that because you know, आपको बताया था कि so the first state is going to be theta, and if the next state is rejected, the second state is again going to be theta. Otherwise, it's going to be theta p. In this way, the whole chain will go on. And number of Monte Carlo Markov chains, length of sample divided by 2. So that could be like 50,000, obviously 5,000, because we have 10,000 iterations here. So this is obviously 5,000. And efficiency kya hai? How many times I have accepted divided by the total number of iterations. So let's see what that gives us, and then row. So let me just. So this might not take very long because remember कि in the hands-on things could get stuck. ठीक है, तो you are supposed to dig this up.
Total iteration.
Yeah, so that means that so we have executed this code. So we have n accept divided by n iters. So that is coming up to be 0.19. And what does that mean basically? Ke 190, right? Or 1900 out of 10,000. So I accepted only 1900 proposals out of 10,000 proposals. Isn't that correct? Yeah, 1900 out of 10,000. So the total number of n accept is supposed to be 1900 only. So that's a very small probability of acceptance. and the row, the last value of row is 0.0, but we have to see the whole. You can plot it, you know, you can plot the whole row. You can plot the values of the new sampled values. वो भी आप plot करके देख सकते हैं. That means के all the values in this you can plot it. बहरहाल अभी हम ये करते हैं कि let's assume के we have this true distribution as post. We set up this 200 points sampled according to 1, and we have this beta distribution, let's say, as the true distribution, because that's what our likelihood board, that was the prior, that was the basically our guess of that. So let's have a beta distribution as the true distribution as well. Just a trial, right? H plus a into n minus h plus b as the parameters, where n is obviously 100, h is 61, and a and b have already defined as for the beta distribution here. So this is also just a guess, you know, just to make the analysis. So I first plot a histogram of type step over 100 bins from the samples, which is the actual theta, and that is the prior. And yeah, so I just plot the histogram of the posterior and the histogram of the prior over the same bins, and I have an estimate also of the true posterior, which is also my own estimate, might not be correct. And then I plot this. So this is my own estimate over thetas. So I can put that as probably 100 points because I'm putting that over 100 bins. So post.pdf thetas, you know, blah 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 blah, and then I can. Yeah. So the posterior that sampled is this. You can see here that the peaks of the posterior are in fact. Do you see a resemblance here? I hope you see that. I hope you see the resemblance here. That, you know, nothing is here as far as the prior and the posterior are concerned. Ditto for here, and this one has probably. If you remember the diagram I showed you when we started this topic, so we saw that this was the prior, this was the likelihood, and the posterior was somewhere in between here. याद है आपको वो? You remember this diagram?
Yes, sir.
हाँ, तो ये चीज अब यहाँ पर हो रही है. Now the point is कि based on the posterior is being influenced a lot by the prior. That's the main thing. But you see at the peak level, जहाँ तक peak का ताल्लुक है, so the posterior seems to be following the original prior distribution. Although we can't, in this scenario, definitely we can't expect both the true posterior and the posterior to be close to each other. ये बहुत ही मुश्किल काम है. ये ऐसा हो नहीं सकता. अगर वो shape में एक दूसरे से converge कर रहे हैं, तो that's a big deal. So yeah, that's my own understanding of this situation. If you are able to derive more, then it is good for you. So yeah, is this thing clear? So I can apply the same for the coin toss problem that we have done in the PyStan case. So we have again in fact, it's the same problem. This is also for the coin toss problem. Start by norm beta blah blah blah. MH coin. So MH coin is doing the same thing as that. It's just simply plotting. So I'm just plotting the convergence for the multiple chains. So I should be able to call this function in which I'm just doing that same thing and calculating. This is my acceptance criteria. This is the same formula. This is exactly the same as that. I'm doing nothing different. Yeah, so I'm again calling the target function. So basically मैं वही काम कर रहा हूँ. But I've just changed some of the, I think, yeah, so I just, for theta in np.arange. So I provide this, okay, I provide these values of theta. So I provide basically 5 values of theta in this. And for each value of theta, I generate a chain, and then I plot the chain. I plot all the samples in that particular chain. Okay. So I have these 5 samples. So I've had these 5 chains because I provided these 5 different values of theta here. So you can see here that all of them are now converging. So that's how the chains are converging. So in this case, it's a very simple problem of a coin toss. So I'm able to show this. You need to remember that we will be typically dealing with a very complicated mechanism in the case of a multivariate distribution. So जब आप real data sets पे काम करेंगे, so it's going to be much more complicated. So that's where the project comes in. ठीक है? Yeah. So this is just another thing. I just have to. We'll skip this for the time being. Just come to this file. This is for the, I think, PyStan case, and I just wanted to show you the formalism for PyMC3. So this is again the coin toss in which we have the beta prior and the binomial likelihood. This a very simple problem to demonstrate. So in the case of PyStan, PyMC, I don't have to specify a model like this. Okay. What we have to do is we have to use this with pm.model, where pm is obviously this thing, the PyMC3 import alias. First I define the prior, pm.beta, then I define the likelihood, and then I say start pm.find map, use the maximum a priori estimate, find basically find that as the initial state. Then I say pm.metropolis. So here I have a very large choice of samplers. I can have Metropolis, I can have nuts, I can have probably Gibbs. मुझे अभी सारी list मालूम नहीं है, but there must I think there are 4 or 5 very famous ones which we can use here. And then the trace is to sample from the from the step and start, to sample from that based on the number of iterations, and that is how this thing is moving about. So progress bar, you have to, so you can show that. Yeah, so this problem was to estimate the probability of acquiring the number of heads. Was the probability of acquiring the head. So we set that as 0.61 as the default probability, and we'll be more clear on how this is being used here in the next class, inshallah, which is tomorrow. But currently, I just wanted to show you with respect to the PyStan case, this seems to be much more convenient way of starting the inference and finishing it. And these are the parameters like we have in the PyStan case. We had these all parameters here, and I show you the value of that. So again, we also have R hat here, which is again equal to 1.01 and similar to that. And the probability density of the number of heads is actually following the normal distribution. Estimating the mean and standard deviation of the normal distribution. So this might take some time. So, but you can say you can define the priors and define the likelihood, and then you just sample from here. Okay, so we're going to be looking at this more in detail tomorrow, not right now. So you see that this is sort of stuck here at 25.44 since a long time. I don't know why. Maybe there is something wrong here, so I will have to debug that. So let's get on that later. So now very quickly I will show you the Gibbs, because we have to finish this today. So Gibbs sampling is a special case of Metropolis Hastings algorithm. The classic Metropolis Hastings chooses a new multidimensional sample point from the proposer distribution. However, if the number of columns is very high, finding the suitable jumping distribution to use can be difficult. Okay, I mean, if you have many columns, then you are talking about a joint distribution, and to jump from one state to another state by sampling over all those columns is very complicated. I can't sample collectively. I can't say sample x1, x2, x3, x4. समझ में आ रही बात की? मैं collectively सारे column की value sample नहीं कर सकता. I can't sample collectively all the values. because the different individual columns behave in different ways, and the jumping width, I don't have that much flexibility. I can't make a long jump. It must be just right for all the dimensions to avoid the slow mixing. It's very difficult for me to sample in one go data from all of these columns collectively to ensure that my jumping width is in a good width. I can't do that. It's very difficult. So that's where Gibbs sampling कहता है कि भी आपको you don't need to sample collectively. You don't sample x1, x2, x3, x4 at the same time. Rather, you sample conditionally. So for example, Gibbs sampling says you first sample probability of x1 given some fixed values of all the other variables. Okay? Then you sample probability of x2 given some fixed values of all the other variables. And in this case, the fixed value of x1 will वो होगी जो आपने यहाँ से estimate की हुई है. Okay? Then you say probability of x3 given the fixed values of all the other variables. Let's say कि हमारे पास 4 variables हैं. So in this case, I have x2, x3, x2, x3, x4. All of them are chosen randomly in the first go. Then in this case, I have x1, x3, x4, where x1 value is coming from here. In this case, I have x1, x2, and x4. उस केस में जो आपकी वैल्यू है x1, x2 की वो यहाँ से आ रही है. So I am basically I am sampling each distribution. I am sampling each dimension separately and using it in a chain to sample from the remaining from the remaining dimensions. एक कॉलम को पहले कॉलम के लिए मैंने रैंडम वैल्यूज के ऊपर उसकी सैंपल की वैल्यू निकाली and the conditional probability in fact, ठीक है, and then I use that conditional probability consecutively in the remaining ones so that I can sample all the conditionals in that way. When I have all the conditionals, I just multiply them and I get this thing. Okay, so just let me write that down so that it will be very clear to you. Yeah, so probability of x1, let's say I have 4 columns. Please pay attention here. Okay, so those 4 columns are x1, x2, x3, and x4. Okay, I cannot sample directly probability the joint x1, x2, x3, x4. It is not possible for me to do that because I have told you the reason. Each column has its own distribution and it is not possible for me to ensure a small jump with different PDs of the different dimensions. Yeah, you should be remembering this. ठीक है, I know कि अभी बच्चे बहुत कम है क्लास में, लेकिन सबका नुकसान हो जाएगा फिर. Please remember this, ठीक है? So I simply cannot do that. Oh, ये क्या हो गया? In any case, let's see. So now, first I calculate. So how do I proceed? I can't. I say okay, first x1 given some value of x2, x3, x4, where x2, 3, 4 are all randomly selected. Okay, I can calculate that. I need to have the condition to estimate the conditional probabilities is much easier than estimating the joint probability. Calculating the joint is not easy. Joint is calculated based on the marginal and the conditional, right? So calculating the condition is much easier. So I can estimate the condition. I can have an estimate for that. So probability of x2 given x1, x3, x4, where x1 is from the previous step. अब देख रहे हैं आप कि previous I use the value from the sampled value now to estimate x2 along with x3 and x4, which are still random numbers. Okay, so now probability of x3 given x1, x2, and x4, where x1, 2 are from the previous step. ठीक है जी. And then probability of x4 given x1, x2, x3, where x1, 2, 3 are from the previous steps. Is this thing fine? I think I've broken this down very clearly now. You should be able to understand this now. So instead of sampling directly the joint distribution, क्योंकि अभी जो हमने Metropolis में जो example देखी है, we don't have that many columns. It's not a very highly multi-dimensional problem, right? A coin toss, that's not a multi-dimensional problem. When you have a multi-dimensional problem, then these sort of shortcuts can come in handy for you. You cannot sample directly from the joint distribution. That is the main problem that we are facing. Oh my God. So in any case, that's क्या होता है यार, वो redo का क्या होता है? Control X नहीं.
Control Y.
Thanks यार. So ठीक है. This is where तो instead of sampling directly from the joint distribution curve, which is very complicated, I can sample the conditional of each column and use it to estimate the condition. When I have all the conditions, then I can multiply them to get the joint. So when I have all the conditionals in this way, then I can multiply them to acquire the joint distribution. Because, I mean, I assume they're independent because they're independent. So again, the correlation between columns is not a good thing. Even in machine learning problems, if the columns are correlated with each other, you need to ensure that the columns are not correlated with each other, not with the label. The intercorrelation should be as minimum as possible. Otherwise, it's going to disturb your prediction. So similarly, यहाँ पर भी यही problem है. आपने MCMC के Metropolis Hastings में भी आपने देख लिया कि यही problem है कि we don't want to sample. We have to remove the autocorrelation factor. That's why we jump sometimes from the one place to another place. ठीक है? So I hope that this concept is clear. Now let's go through the slides very quickly. Yeah, so Gibbs sampling, so now you will understand in a better way, involve choosing a new sample for each dimension separately from the others. I sample each column separately from all the other ones, rather than choosing a sample for all the dimensions at once, which is very difficult. So I do that based on the conditional probability. The problem of sampling from potentially high dimensional space will be reduced to a collection of problems to sample from small dimensionality, because I'm using each column independently of all the other columns. That's the main logic behind this. So just look at some maths. So obviously I don't know the joint distribution, okay, or it is not easy to sample directly from the joint distribution, but the conditional distribution of each variable is known. That is the requirement in the Gibbs sampling case, and this is easily applicable in probabilistic graphical models. It has a reasonable computation time and memory requirements since they sample one random variable at a time. Okay, so these are some of the logistic information. So this is the basic example जो कि आपको blogs में और books में in fact मिल जाएगी कि you can sample from the normal distribution. You have a joint of two variables x and y, which have a mean. Each value, each x and y has a mean of 0 and a standard deviation. The covariance matrix is this one between the two. This is the covariance matrix which you also have to work with. So probability of x given y is easy, and probability of y given x is also easy. So based on this particular problem, I can just sample it, and I can show that the joint distribution is sampling the points in this particular area. That's a very famous blog. ये मैं आपको कल इंशाल्लाह ताला दिखा दूंगा. So based on this problem, if both x and y are following the normal distribution, then I can easily show that the Gibbs sampling based on the conditional sampling is going to remain within this oval circle here across the boundary, around the boundary. So the idea is sample x comma y, that is my problem. I cannot solve it directly. So first I sample x given y, and from that I sample x, y given x. So now I have both these samples. I use the samples to sample the joint, and then I can proceed ahead in that way. So probability x given y is this one, and due to symmetry, y given x is this one. Simple. And the value of x here is basically coming from this point. A new sample is when a new value for both x and y have been generated. So that becomes, obviously that is my new sample because I'm looking at the joint. So when I have a new value for both x and y, then I have the, ये उसकी कुछ if I sample in a particular region, then the Gibbs sampling can get stuck in a region. Also, I can have some probability spikes, and I can't avoid those spikes. So ये दो उसके problems हैं जो Gibbs sampling के आते हैं, but we don't need to focus too much on them at this stage. So this is the same thing. You can use Gibbs sampling, θ1 given θ2 and θ2 given θ1. So sample first of all θ1 from this conditional distribution, θ1 given this. So I have a distribution here and I sample the value of θ1 from that. So it could be the normal distribution, okay? And I have a distribution here and I sample from that to get θ2, but here I use the value θ1 which is here. Okay, so the conditional of θ2 is depending on the value θ1 which is sampled from the previous timestamp. That's it. इसमें कोई आपको कोई लंबा छोड़ा रहा, ये वही एग्जांपल है जो मैंने आपको बताई है, with the mean of 0 and a covariance matrix, this one. So इसकी मैं आपको hands on दिखा दूंगा. This is what it generates. So this is the joint distribution, right? Like, so we have we have the value x here and we have the value y here, or θ1 here. You can use both the terms, θ1 here and θ2 here. Yeah, so this is, it just remains in this area, but you can see that we have a few outliers as well. So that's not what we want here. So we have to be very sure of these points. The p equals to 0.9, where p is one of the parameters that we use, and this is how we call this a full conditional distributions. Gibbs sampling can be used when the other methods do not work well, typically in high dimensions, based on the conditional distribution. So you are required to use that basically. So we sample each variable in turn, condition on the values of all the other variables. It considers a Markov chain where the probability of the next sample is calculated as the conditional probability given the prior sample. So yeah, so next sample की probability क्या है? That is not the normal probability, but that is the conditional probability which is given the prior sample. Samples are constructed by changing one random variable at a time, meaning that subsequent samples are very close in the search space that is local. हाँ, अब इस केस में प्रॉब्लम यही है, because I'm sampling at each time step, I'm required to sample from each column separately. So I am likely to remain very close or very much correlated to the previous point, because I'm moving like an elephant basically. I'm moving like an elephant, so I'm not likely to make a very high jump. So ये थोड़ी सी उसकी limitations हैं. As some, there is a risk of the chain getting stuck. Only applicable for discrete PMFs, which allows sampling from the conditional distribution. You have to see where this thing is applicable, in which I can sample directly from the conditional distribution. So just a bit about this. This is one of the other experiments in which we define two Bernoulli functions. One is the normal function I calculate, and the other is the typical Bernoulli function. I just returned it. This is the second one. I just create some numbers and then make a plots. I generate the number and create the mesh grid. So now in this case, the prior is the beta, AB into PDF of X and PDF of ये joint prior आ गया. You see, this is the joint prior, and the likelihood I'm using, the likelihood function is burn 2, which is here, क्योंकि मैंने खुद sample किया है, and the posterior is stats.beta.pdfx into stats.beta.pdfy. So ये basically directly वो कर रहे हैं, prior and the posterior मैंने खुद estimate किया है. So if this is just the analytical solution. This is not a sampling solution. So the prior goes like this. This is the mesh plot basically. Joint, आपको joint distribution plot करके दिखाइए यहाँ पे. You can use the same formalism here. So this is how the prior distribution looks like in the joint case. Likelihood function is here. The posterior is like this. So you can see that these three are like seem correlated to each other in shapes. And I mean, if you want to see that in 3D, so the prior is like this, the likelihood is like this, and the posterior like this. I mean, this is very similar to how the the three curves that we saw initially when we started the code, right? Then we go ahead. So this is another function, C2D, in which I'm calculating some area here. So still we are here. So this is again the analytical solution. So this might not be very important. So now for the Metropolis case, we are generating the prior likelihood and posterior. So you can see the posterior, I mean, it's done a good job. I mean, मैं ये नहीं कहता कि इसने बेड़ा गर्क कर दिया, but looking at these, you know, we still, this is the one of the you know, one of the outlier points. So the posterior, you know, you need to work with these values to improve the posterior. That's the thing. So prior to the likelihood, you specified yourself, and just let me do the Gibbs one. What I said, the prior and the likelihood, this is where the Gibbs condition is coming up. So I'm sampling the one based on the other one, and now we can see yeah, so you can see the posterior here in this case is much better than the you know, the posterior for the Metropolis Hastings algorithm. So yeah, so that's how it is. I mean, this is a very simple problem. I mean, we are not dealing with very complicated problems here. So कौन सी चीज किस चीज के लिए चलती है, we don't know. Okay? So that's the thing that you need to keep in mind. अच्छा, sorry about that. So we come to the end of the lecture here. So we basically finished this topic of MCMC, which was quite complicated. You do understand now how the MCMC process works, especially in the case of Metropolis, Hastings, and Gibbs. There are other algorithms as well. We need to do more hands-on here. Like I told you, we are going to be seeing some example. We're going to see this. You may be developed on the island example. This is a childish example, but we need to work with more complicated data sets. We also need to work with this. So I'll just stop this. Okay. So we also need to work with this MC3 library. You know, we can estimate the parameters of the linear regression model using PyMC3, alternate formation using the generalized linear model, and we can also estimate the parameters of the logistic model using the same mechanism of MCMC, and we can do much more. So I'm developing this. So we are now terminating with that. The point was to explain to you how this thing works. So now we are absolutely, I think, crystal clear on the point how this sampling is being done. That is the main thing. Metropolis Hastings समझ लिया है, Gibbs समझ लिया है. I think that is enough. If there are algorithms which are in extension, then we have to see their parameters. So for example, we can see yeah, so it's the effective no U-turn sampler with dual averaging. Okay, so उन्होंने बताया था कि for this sampling purposes, how to combine the likelihood and the prior. So a lot of things are being done. So you can basically use that to you know, to try out and different things what is actually happening. So this is the inference, the posterior predictive functions. We need to go into the details of these PyMC3 library. अभी तो हम बहुत superficial level के ऊपर हैं. I think we need to go into the details of this. So all of these parameters you have already seen: draws, step, start, trace, chain, tune, model, random seeds, callback. इसको समझना होगा कि किस तरीके से इस्तेमाल करें. So obviously we'll see that in the next class, and I'm going to give you a huge assignment now, जिसमें इन सब चीजों की वो हो, and obviously I have to give you the project as well. In this case, we have a few topics which are still left. So these are the main topics which were needed to be in fact covered. You got the nuts, you got the HMC, which is the hierarchical algorithm, the pure Metropolis, binary Metropolis, binary Gibbs Metropolis. So it's a combination. Categorical Gibbs Metropolis, DE Metropolis, D Metropolis, slice, So I mean, we need to see कि ये क्या हो रहा है. All of these things are there. So you need to experiment with this. Okay, any questions?